So today we're going to be talking about the shell method here. Just a different way of finding volumes. Joke here is the shell method preferred by Donatello, Leonardo, Michelangelo, and Raphael. Ninja Turtles everywhere. The formula for this is, if you want to spin something around the y-axis, or vertical axis, here's the formula. It's the integral from a to b of 2 pi times the radius of x times the height of x dx. Now what this looks like is, instead of making disks and disks and disks, we're making shells that fit into each other. So it looks kind of like this here. So it's a shell here, then another shell in there, then another shell in there, then another shell in there. They kind of fit inside each other. Like those Russian Kachina dolls. I'm not sure if that's said right or not. Nesting dolls that fit inside each other. That's what we're doing. It's also kind of like a lightsaber. I think you could use this in a lesson. So yeah, we can find the volume of this shell, right? And this shell, and this shell, and this shell. And we can add them all up to find the volume of the whole thing. We did this some years ago. Hours upon hours of work. So, but you can see the shells here built up from it. And this is kind of what it would be. You can see all the corrugated cardboard here, just shell, another shell, another shell, another shell, another shell, just over and over again as they get bigger and bigger and bigger. Now this isn't the technical way that this is figured, but if you want to look at the technical way reasoning for this, you can. Here's the way that best I find students understand this best, and here's the way I understood it as a student. So we're going to start with, of course, a box, right? And the width of the box is going to be the dx, and the height of the box is going to be h of x. Height of the box is going to be h of x. Now, what we're going to do is we're going to take this box here, and if we're going to revolve it around a circle. If I revolve it around the circle, well, what's the distance around a circle? Circumference, which is 2 pi r. 2 pi times the radius. If I want to add them all up, that's where the integral comes in, from a to b. So h of x and then the dx right there. So that's how I think about it. The great thing about this is we can spin things around a vertical axis, but still do it in terms of x. And we like x. So, example is going to be this one right here. Find the volume generated by revolving the region bounded by y equals x minus x cubed and the x-axis about the y-axis. So x minus x cubed looks like this. So we're going to spin this around the y-axis. So it's going to be looking like this. So that's kind of what it would look like here. We could do this using the disk method, but we'd have to do it in terms of y. So we'd have to be finding the height of these. Problem here is, to find the height of this, I'd have to break it up into two piecewise functions to get the outer radius minus the inner radius. And that starts getting gross, doesn't it? So we'll just avoid the piecewise functions things and do it this way. So, here's our axis of rotation. I'm going to put a little box in here, another one over here, because this is the one we are spinning around. So when we spin this around here, what's the height of this shell going to be? Height of the function. x minus x cubed. From here to here, just the y value right here. So in this case, h of x is going to be x minus x cubed. The radius of this thing. The radius is changing though. The radius of this isn't always, I mean right here, that's a small radius, correct? But over here it's getting bigger. Over here it's getting bigger. What's the radius? Well, it's always however far it is from here to here. In this case, the radius is just x. The radius is getting bigger. So as the height's getting bigger, the radius is getting bigger too, but it all works together. So in this one, the radius function is just x. So we set up our interval. Let's see here, we're going to go from 0 to, that's 1, 0 to 1, 2 pi, the radius is just x, the height function is x minus x cubed, and the width of each box is the dx, because they get really, really small. Is that something we can anti-derive pretty simply? Yeah. Very, very easy to anti-derive that. So the people who just came in here, what we're doing here is taking we have to spin around like the y-axis we normally like to do in terms of x, but what we can do is we can make shells. So I can find the volume of this shell, right? In this shell, in this shell. I can add them all up, and it'll give me the volume of the whole thing. Mm-hmm. Like this one too. I can find the volume of this shell, really, really tiny. Volume of this shell, volume of this shell, this shell. If I found out all the volumes in between, add them up and get the whole volume. Think of this one. All these little shells, just adding them up. So, the way I explain this is, for this shell here, I can find the radius of this shell. But this is, if you look at a cross section of it, of each shell, it's just kind of like a box, isn't it? Where the width is the dx, and the height of it is just the y value. Now I'm going to spin it around the x-axis, or something, some radius, and if I spin it around, that's the 2 pi r. It's going around the circumference. But integrals just have us add them all up. So, now there's a different way in the book, guys, but that's okay. Book teaches a little bit differently. My way still works. Still mathematically correct, but it would take a few more steps to do. Anyway, from here we could just anti-derive this and solve it. What we're going to do now is we're going to take this, we're going to spin it on something other than the y-axis. So what if I were spinning around something over here? What would the radius be then? So let's spin it around. The line x equals 5. So this is x minus x cubed. I have a shell right here. This is 1. Here's our axis of rotation now. So our shell's going to be looking like this now, isn't it? So we have this going around here like this one over here. And our shell is looking like this. height of this thing is going to stay the same. Height of it is still x minus x cubed. X minus x cubed there. That part's not a problem. It's what's the radius going to be? How far is it from here to here? Because it's changing, isn't it? As x gets bigger, the radius here is actually getting smaller. So how do I deal with that? Well, we take a small step back, actually a big step back, into geometry. Something called the segment addition postulate. If I know two parts, they add up to the whole, right? Total is the sum of its parts. So the radius of the whole thing is going to be what? Pi. Now how far is it from here to here? Now, that radius is moving, right? Well, this is just going to be, right here is just going to be x. That's all we want. We want this part, don't we? So our radius is going to be 5 minus x, right? That's it. So radius here is just 5 minus x. Now the area we are integrating to find the shells up is still 0 to 1. Now we got 2 pi, the radius function, 5 minus x. Then we're going to have x minus x cubed. That's the height of it. The width of each shell here is the dx because it's infinitely small. Once again, this is just a nice polynomial. We'd have to, distribute. We can kick the 2 pi out front to the end. But this is how you set them up. The great thing about this is, if you have to spin around the y-axis, it allows us to do in terms of x, and we prefer that. We like that a whole lot better. So we have trouble flipping axes. The human brain has trouble with that. That's why people go into space. Sometimes there's no orientation, so people get sick. So, all right. So that's the shell method. What I'm going to do is I'm going to give you some cards trade cards, just to look at them and set them up. How would you find the radius of this? How would you find the height of the box, etc. But that's the big idea behind the shell method. You kind of have your choice. We still could have done this with the washer method. It just would have taken a whole lot more work. This is just a different way of doing it. Sometimes it'll be set up easily for the shell method. Sometimes it'll be set up easily for the washer method. It's kind of your choice how you want to do it. AP exam, all the problems are written so that you can do it using the washer method. The shell method is not on the AP exam. It'll be on my exam, just not the AP exam. So you will never see. Now, let's say you go brain dead in the middle and say, hey, I forget how to do the washer method. I can do this long, complicated way of doing the shell method. If you were to do that, would they give you credit for it? Yes. Yes, as long as you set it up correctly and do it correctly, yes, they would still give you credit for it. As long as it's a valid solution. So, all right.